All right. So, first of all, thank you, ODSC, for having me over. Today, I'm going to speak about our AI platform to mine competitive intelligence from billions of unstructured online sources. A bit about my background. I have been fortunate to work with the best minds across academia and industry on a lot of large-scale AI platforms ranging from different applications from behavioral advertising targeting to recommendation engines to knowledge management of the robots in a human environment. And finally now at Meltwater, trying to create the world's biggest structured data source from external data. A little bit about our company. We are in the B2B. Not many people might know about us. We are a global leader in the media intelligence space. We originally, we have a lot of humble beginnings. We were bootstrapped with no venture funding. And over the time, I've expanded into more than 50 offices across 6 continents. In short, what we do is, we are a big data company, like most of you guys are here, right? But the type of data that we try to extract and mine insights from is slightly different. It's mostly coming from external data. So in short, we process hundreds of millions of documents every day, and they're responsible for several orders of billions of searches that are used by our end customers. In short, we track leading performance, right? We take all this unstructured web data that is out there, try to compute things like brand perception, share of voice, competitive intelligence, client satisfaction, and all of these are disseminated via a product suite that we have, ranging from web applications to mobile suites to news feeds, right? So far we have onboarded 28,000 corporate customers. More than 50% of Fortune 500 companies use our SaaS products for doing the brand and competitive analysis. Under the hood, which is what my talk is going to be primarily structured after, right? We at a very 10,000 high-level overview, we do we do ingestion using AI-driven crawling to take the unstructured web into converting into relational tables. So as I said before, we process around 100 million documents. We do a lot of data augmentation because unstructured web can come from varying in different languages. So we do natural language processing and information extraction in 15 different languages. We build a knowledge graph so that we embed pretty much all the factual knowledge that we extract from this external web into a structured knowledge base. And most of our media intelligence applications, right, they essentially sit on top of this gigantic data index and the knowledge graph to do things like counters, aggregates, drill downs for vertical search, newsfeed applications, anomaly detection, trends, influences, etc. So before I jump into explaining our platform, the main motivation for our platform has been, in order to drive most of our insights, what we call as outside insight, we need access to clean, structured outside data, right? Unlike most BI systems where data is already, the schema is well defined within the internal data stores, for people who work on the external web, most of it has implicit schema, right? And it's not very well defined. It's not meant to be stored in the relational tables. So we want to make sure that the data is clean, it's normalized, it's easily accessible for our data scientists. And sometimes you can actually get very deceitful data, right? I'm always amused by this site that shows spurious correlations that can occur. I think it says something like US spending on sciences directly correlates with suicides by hanging and strangulation, right? You get extremely spurious correlations if we don't have a way to systematically mine the factual knowledge, right? So we need to be able to reason the insights that we are showing to our customers to have a high quality impact with those insights. And again, as most of you guys know, most data scientists spend their time in data plumbing, right? If you look at the survey up there, it says that more than 60% of the time actually is in trying to calculate, in trying to actually plumb the data, right? The data is not in the right way for them to start doing analytics on. So that's essentially what our platform tried to aim for, create a well-defined structured data store out of the outside data. So this is how our stack is actually set up, and I'm going to cover the bottom part, which we call as internally referred to as fair hair. That's the name of our platform. It has 4 building blocks from our AI-driven crawling to our enrichment platform to the knowledge graph and all the APIs and search analytics that we have that can be powered by a lot of our product suite that we currently have. Before I mine into why we need to dwell into AI-driven crawling, right? There is a lot of external data that is out there. I think people have been barely scratching the surface by giving like this, media analytics on online news and social media. Those are the obvious ones. But you can actually have interesting insights in financial filings, the actual corporate website, looking at the advertising, looking at how your competitors are doing with respect to what types of jobs they're hiring to understand how the strategy is changing over time. And all of these different data sources are differently structured, right? Because they serve different use cases. And as you know, most of the information that we can mine from external web, it can sit inside DOM. That's essentially the page structure, right? You can extract information from all the unstructured text that that we see on the web. There is a lot of microdata. These are the human annotations these are the human annotations that are compiled by the site publishers to make their site discoverable. And there are a lot of tables where you have relational data from which you can compute information from. So the first part of the presentation, I'm going to talk about our AI-driven crawling, which mainly talks about our web extraction and the site microdata. So before I jump in there, this is how I treat an academic web base. The Google's, Ellen Halevis of the world, they say that, hey, this has been a solved problem. We have semantic web, we have microdata, and pretty much all the information that you can mine is in web tables, right? And you have like very well-defined APIs to give you the structured data, which means that they have, there is a good, beautiful house that is coming up as a templated website from the internal data store. But in reality, this is how the real web is. APIs are limited to very, very large websites, right? And the marginal information that you can actually find from web tables and microdata is pretty minimal. We have some stats that back it up. And the real problem is not with a one-time extraction, right? But keeping the data up to date over time is also a challenge. So that's when we started looking into investing into AI crawlers, when we moved past just the news as the primary source for our intelligence business, right? And to give a bit of a background about web extraction, traditional scraping methods require a large amount of human effort because you're trying to extract structured attributes from the sites, right? And either you can write code wrappers. These are like complicated regular expressions to express what from the called wrappers, essentially, which are essentially like a small agent programs that can extract meaningful information from a website. And usually these wrappers are really, really hard to manage. They fail all the time. Then there have been companies who started building UI tools so that people can essentially annotate the web pages that automatically produces the wrappers. Again, even for this, in order for us to scale to all the sources that I have shown in the previous slide, it takes a lot of time, right? And the recent advancements, there has been some advancements in the automatic scraping where you essentially use AI to learn from data samples to produce those wrappers that can essentially go and extract information, right? This is what we call it as a fully automatic web extraction. There are some companies out there that does a good job for structured, for a fixed set of data types. But when we really have to scale to the type of data types that we want to go after, we need to have our own in-house AI crawling team, right? To just give an example, before we invested in this, we had more than 50 engineers who were day and night writing regular expressions, trying to maintain the sources. Half of them were failing all the time. It takes each source takes 1 to 2 hours to fix. But what is the problem with the wrapper induction to make it really, really web scale, right? I'm sure you would have heard that maintaining these wrappers is usually a very hard job because sites change all the time. So our goal was to minimize the supervision that we do per source. But one thing we can afford is we can take prior knowledge. We know how some of these entities are expressed, how these entities have a certain type of relationships. We can use this prior knowledge from existing knowledge bases so that you can combine the hybrid. It's a hybrid of AI engine with a machine learned domain-specific classification. So you actually train the AI engine per domain by giving some few set of examples to learn the wrappers. But the other problem is, application of this prior knowledge can be very, very expensive because, you don't have ontologies that are defined for every site that is out there, every domain that is out there, which means that you will essentially end up having a bit of a noisy ontologies. So, for that, the answer is, we go, again, domain specific. We learn from few examples of the sites, right? We generate these AI wrappers. We start using those AI wrappers to do full site extraction. So in this way, we can easily translate the last few layers of our wrapper induction from one domain to make it adaptable to the next domain. So in short, what we have is we have a framework for rule-based feature engineering, supporting quick turnaround for domain-specific rich features. We have like almost 2,500 built-in features to represent structure, visual rendering, and textual context of the web pages, along with the sitemaps that will help you navigate to the site. Needless to say, we also have to put in a lot of work for actual exploration, template discovery, domain modeling, form understanding. There's a significant amount of work that actually went into really trying to automate all the wrappers we have. So the result of that is, for example, on the left-hand side, you can see a news page. The job of the crawler is to go and fetch this news and convert into the structured data that you can see on the right-hand side. As you can see, it tried to extract, in this case, it is extracting the actual body, the title, the publication date, who the author is, which news article it's coming from. And then I also highlighted the fields that we have extracted from the microdata. These are the keywords, summary, site handles. These are the ones that are not actually visible in the site. These are the ones defined by the human to make it compliant to either schema.org, some of the semantic schemas like Facebook, OGP, etc. But there is a lot of information that is actually kept in these fields, right? And you can imagine the type of information that you can actually mine by looking at this JSON structure. So, after a heavy amount of work, where we are finally seeing the results to pan out of our AI crawling team, now we actually spend 80 to 90% less amount of human work to adapt to new domains of websites. We are able to extract a lot more structured attributes. We have seen like 10x number of attributes, and the biggest thing is, now we have more than 30 million sources that are being crawled from the external web. So we saw this huge increase, like 100x increase in the number of sources that we are going in the last 1.5 years when compared to what is that we have done over the last decade, right? So the amount of explosion of the number of sources is mind-boggling with it. The next is, as you saw, most of the information that we get from the web is in the form of natural language, right? So one of the things which we really have to invest is in actual information extraction. And Meltwater as a company cares about providing intelligent insights about companies, products, brands, key decision makers, right? So so we really have to do a good job in identifying these entities and disambiguating them, and understanding how the relations that can exist between these key entities. So in this example, if you see a sample text, we do the usual full NLP stack of syntactical analysis. And then we identify that Tesla is an organization, SolarCity is an organization, Monday morning is an event time that needs to be extracted. But Tesla can mean multiple things, right? It can mean either the Tesla Inc., which we all know, but there is also a Tesla, which is a Czechoslovakian company that is out there, and there is a Tesla Science Center, right? So we need to understand which Tesla this natural language text actually means. So for this, what we need to do is called as a name entity disambiguation, where we take the named entities, use the contextual features that you're retrieving from the text, embed that into our knowledge graph to understand which particular entity this actually really means. And the motivation for doing this is we want to map out all the known structured entities we care about. Like, we have almost like 12 million companies in our knowledge base. We have like almost like more than 1 million key influential people. We want to understand what kind of events and relations that exist from all the unstructured text that is out there. So once we disambiguate the entities, we essentially apply a relation extraction so that an edge can be added on top of inside our graph, right? In terms of NER, so name entity recognition is not people have been building this for a while, right? And there are a lot of toolkits that are out there that gives you out of the box NERs. But the problem is, when we look at data that is coming from different domains, right? We need to build very, very domain-specific NERs so that we do really good job at identifying the entities. And previously, we were essentially taking a lot of syntactical parsing inputs, doing a lot of feature engineering out of it, doing some parameter training, apply CRF, like that's one of the most popular sequence labeling algorithm that is out there to do NER. But we started experimenting with actually injecting LSTM in between. The reason is, first of all, we don't need to do any sort of feature engineering, right? And the other big advantage that we get is, in order to do transfer learning, to adapt our NER to new domains, it's pretty simple. We just have to strip out like the last few layers of the LSTM, and then you readapt it to a new domain, right? So in that way, we are able to generalize the NER model that we are building. So in this particular example, if you see down, what we're doing is we are basically embedding characters, we are embedding the brown clusters, the gazetteers, and the actual words. But then, because with the explosion of the mediums of the data that we're looking at, sometimes you see all these funny characters. You see new words, you see new dictionaries coming out of these different types of sources. So the character embedding is one of the strongest things that you can look at. And in order for us to actually model it much more better way, we started actually doing character embedding via CNN. So what we do is, this is inspired by one of the recent advancements in NLP. It's a paper from ACL 2016. So what they do is they first send the characters through a convolution neural network, and the output of the neural network is actually sent through an LSTM. The output of the LSTM is then sent to a CRF to actually do the entity recognition, right? And of course, in order for us to adapt to our particular vertical, we need to play with the different embedding size, the optimizers, the dropout rates, and we got some significant improvement, especially in terms of the amount of time that it takes to go from one domain to the next one. In terms of the disambiguation, again, we have a known knowledge graph, which I'm going to talk about. We convert it into a triple store, and we use an open source framework called Agdistis. It's an open source framework for doing NED on any open knowledge graph, any linked graph, right? It's a combination of hits. Hits is short for hyper-inducive topic search with the label expansion and string similarity metrics, right? So essentially, you get the plain text, you extract the entities out of it, you extract the contextual features out of it, do a graph walk in order to identify the right, in order to disambiguate the right entity, right? In terms of the hits algorithm, it's essentially pretty much like a PageRank variant, right? It's with some key differences which are highlighted here. It's very, very query dependent. That means that the hubs and the authority scores can result in different scores depending on the query you're using, right? It is executed at the query time rather than the indexing time, like the PageRank use case. It computes 2 scores per documents, hub and the authority, as opposed to a single PageRank score. And it is processed on a very small subset of relevant documents in the graph. So it first tries to isolate the part of the graph that it needs to look to do the walk before actually applying the disambiguation algorithm. So, but the problem we had was, the original Agdistis was only receiving named entities, right? So the disambiguation context was very, very hard. As I said, since we care about very, less number of entities, like people, organization, and brands, but very, very high quality entities. But that means that we have lesser number of contextual features that we can use during the graph walk. So what we did was we essentially complemented our NER with domain specific terms. The first thing we adapted was into the business domain, where we started capturing the business terms using term bank generators, right? Like a usual NLP term bank generators, and use all of that for the contextual search of the entity. The second problem we had was, we have like a nice English knowledge, English NED, but how, we have like more than 18 languages that we want to do analysis on. But the good thing is we represented our schema using the Wikipedia schema, which is the DBpedia schema, and extended the schema with our own ontology. So now we are able to use the underlying mappings of DBpedia that exists across the languages to do the walks on other languages as well. So now we are able to extend our NED to more than English, although English is the most richest language features that you can get given the index size, but we are able to do a pretty good job at doing NED at other languages as well. The next comes RE, which is essentially our relation extraction, right? We get these documents, we send it through the usual tokenizer and the sentence splitters. You select the probable sentence where you can find the relationship and send it to 2 different relationship extraction modules. One is a LSTM one, which I'm going to go over, and the CNN relation extractor is very similar to what I explained before. And the output of this is fed into a Stanford relation extraction, which gives you the actual relation that exists between these 2 entities in the documents. So the architecture is pretty simple. We take the input sentence, we essentially convert that into glove vectors, which is like the next generation for the word to vec. And the reason we actually start embedding vectors is when we want to translate this from one language to another, we can build our own sort of glove implementations, right? We have a humongous corpus of documents using which we can take these embeddings. And then we give it into LSTM. I think this LSTM has few hundred units, and we use the softmax as a decoder to essentially get the output. which is sent to the actual relation extraction, right? We saw some really good, F-score numbers when we actually started using LSTM as a way to adapt from one domain to the other. The next is knowledge graph. So once we get all these facts, remember that we have 200 billion documents that we have captured over time. We get a lot of entities and a lot of relationships that can be mined over it, right? And we look at a lot of data sources to build this graph. The challenges are very simple, right? The figure on the right is I borrowed from the Lunadong's paper from the Google. They also built a knowledge vault using all the sources that they have crawled over time. And from each of this type, they were able to extract a lot of facts, right? From DOMs, they were able to extract more than 1.2 billion facts. From text, they got 300 million facts. But there is also a lot of intersection, right? Where the lines between those boxes actually mean these are the intersection of the facts they have seen across these sources. So now, which fact do you trust? How do you assign confidence value, right? And how do you take care of this deduplication, right? That's when you really have to start using machine learning on top of these extracted facts that we have inside a graph to give probability assignments. For that, we looked into graph embedding. Essentially graph embedding is you give the input as a graph of relations, and the goal is to produce a low-rank tensor factorization of the co-occurrence cube of all the combinations, right? And all it tries to do is it minimizes the scoring function that is described here. This is very well described in a lot of literature. People have been building knowledge graphs for a very, very long time. And then there is another concept called link prediction. This is how do you assign probability scores for the links that exist inside the graph, right? Again, here what you have to do is you need to train, you need to annotate, you need to tell the system that, hey, these are the known examples of tuples, and these are the false examples of relations that can exist between these tuples. And the system iteratively mines with these positive and negative rules to assign what part of the source is contributing to how much truth within a given graph, right? Essentially, it's setting up a decision boundary for the truths and false. You can use the standard regular classifiers, right? Like we used random forest, I believe, and use this embedding as a feature. So what it does is, for example, in these two different places, there is a weak indicator path. So inside the graph, let's say that we want to see if Mercedes is competitor of Volkswagen. And then, yes, they are both connected to Germany as a country, right? But that's a very, very weak indicator path. But the system needs to understand that this is a weak indicator path. And then there's a strong indicator path. They are both competitors because they essentially produce car engines. So how do you teach the system to infer these kind of rules, right? So with the positive and the negative rules, you will be able to give like probability assignments of the source contribution to the truths and the source contribution to the false. And our contribution here is essentially we combined this path ranking algorithm with the embedding model to produce a slightly superior scoring and prediction algorithms. So the current state of the art is what you see in the blue here, and the red is the actual AUC, area under the curve, that we received by actually combining these two methods. So as an output, we have all these 200 billion documents. We embedded several billions of points from it. And we managed to produce 275 million unique, distinct facts that are with extreme high confidence. So we mapped out close to 11 million organizations, a million people, and that's a snapshot of the number of instances that we have for each of the relationship type we went after. The good thing is, we used Gremlin as a way to express most of our graph analysis queries, because of which we are able to swap out the underlying graph stores, which are meant for both the OLAP and OLTP. There was no one good graph solution that is out there. So while we are experimenting with that, we still wanted to make advancements here by writing it in Gremlin that helped us to move from one graph store to another very, very easily. But now, let me share you a little bit of practical learnings of how we scaled all these NLP and information extraction pipelines, and what is the platform that is needed to build these insights. Right? So as I mentioned before, with these 200 billion documents, the goal is to essentially give a very good pipeline platform so that both natural language processing people and also data scientists can build intelligent applications, right? So we have two layers. One is the analytics layer. It's a no-brainer. We went with the Hadoop ecosystem. Like pretty much all the data is parqued in a way so that you can run like gigantic Spark queries for analytics. And then we have an Elasticsearch serving layer. There is a lot of work that actually went into scaling Elasticsearch to this 0.5 petabyte of index. and supporting billions of queries that are currently being done by all our applications, right? As an example, this is how complicated NLP or information extraction pipeline looks like in production, right? It's never a linear ETL, right? You have forks and joins, right? And then you have like conditional routing so that you can actually conditionally route based on the output of the previous step. And if you look at the infrastructure needs, each of those modules have different infrastructure requirements. One is a very GPU heavy one is a heavy memory intensive, one requires a lot of compute. They have different scaling needs, right? But they all operate on this document stream that we ingest over time. We're ingesting more than 100 billion documents. And at the same time, each of these modules are built by different people, right? And these are like data scientists, research scientists who are producing these models. Very much like our software code, they also have a concept of the version of the model, right? What data set has been used, what training parameters have been used, what sort of goal set they have validated on. All of these are stored in a centralized repository, and these models are actually, it's a collaborative environment across all the data scientists that we have, so that whenever they produce a new model and gets pushed into the production, it automatically applies on the goal set of data to see how is that they have done. So it's essentially like a testing framework for them to understand whether they have a meaningful increase in the models that they're doing on the production or not, right? And I know that there is a lot of work that actually went into this, and I know there are companies that are out there who are helping people to setting up these pipelines. You guys should totally look into it. But in our case, we built our in-house proprietary system, right? Which means that essentially we have this collaborative enrichments as a service. As I said before, we interoperate with all the state-of-the-art external enrichments. It's a data wrangling platform. We take care of the provisioning, deploying, and scaling of the internally trained models. And we have a registry for the lifecycle management. And right now in our production, we have almost NLP in 15 different languages with 10 to 15 different DAG pipelines that I have shown in the previous slide. Human in the loop, to produce a good quality model, you need a really high quality annotation data. And as you know, training data gathering is really, really hard. There are companies out there who are simply focusing on the training data, right? And we have to annotate text, we have to annotate HTML, we use it for entities, we use it for classification. There are a lot of tasks that we do. We worked a lot on trying to understanding which of our annotators needs to get what tasks, like ranking and the inter-agreement. But with the recent advancements, right, with the deep learning, we try to remove the feature engineering as much as we can from most of our modeling. So recently we started exploring into, is there a way to where we can actually produce noisy training data, but somehow use that for our use that for actual training. So there is an awesome software out there. It's called Snorkel. It's by Stanford University. So what their thesis is very, very simple. Instead of trying to produce the actual labels, you can bootstrap the training data with labeling functions, right? You can use an existing knowledge base, or you can actually use labeling functions to give out labels on a large corpus of documents. And then it produces a whole bunch of heuristic labels, and you'll be able to model the noise using a generative model, which I'll explain soon. So essentially, we already have a knowledge base. We already know the known relations, right, which we can consider it as a goal set. Take this knowledge base and just annotate all the documents wherever those entities exist, for example, right? And use that as a noisy training data. So, it's a three-step process. People write labeling functions, the scripts to label all the data that we have. These are small scripts that can be executed as lambdas, right? And then we build a generative model. Essentially, what we're trying to do is, we look at the marginal likelihood estimate to learn the joint distribution of the data and the latent labels. And then you can use any of the noise-aware discriminator model like LSTM to actually train your model. The caveat here, or one thing to remember here is, in order to produce a good generative model, you need to have a substantial amount of data on which you apply these labeling functions, and there needs to be a strong overlap between these labels, because essentially you're trying to model the noise, right? So if you have like very, very small data sets that are available for annotating, this is probably not the way to go. But if you have an existing knowledge base, if you want to use like distant supervision on a large corpus of data, this absolutely works pretty well. In terms of a sample building of an insight, because we, as a share of voice is one of the biggest features that we have, so we need to give out sentiment on all the documents that we push out, right? And as you know, a full document sentiment is pretty deceptive because there is a lot of context that goes into it. So we invested a lot in what we call as aspect level sentiment extraction. And there are two parts to it. One is the actual character level embedding, where we use a multiplicative LSTM encoder to essentially understand the sequence of text that is being passed. And then on the other side, we have a traditional NLP methods to essentially compute the aspects that are relevant for our customers, right? So we take an input sentence. We essentially take just the UTF-8 encoded bytes, right? Send it through the encoder. One of the units actually gives you a score between -1 to 1, right? And that's how you know how much each character in a sequence is contributing to the sentiment of a document. But for this, in order for this to work, you need a really large amount of training data, because we are trying to model how these characters, when they're sequenced, are producing positive and the negative themes within a review. But since we have a large amount of corpus, we took almost 100 million online reviews that has star ratings, right? 5-star, 4-star, 3 stars. We use that as a weekly labeled data. But we gave like 100 million reviews. We essentially gave like 128 batches to the LSTM. This is a model that has been trained for over a month. It took us more than a month to actually train this model. But now it's a very rich model that can actually work pretty well on different domains. Even though we train on online reviews, we're able to use it on the social data. We're able to use that on a sentence level data that we get from news documents, right? And in terms of structured aspect extraction, this is a known field, right? We use a variety of traditional NLP techniques. We do normalization, tagging, we do noun chunking, NP clustering, segmentation, and generalization, right? And finally, what we extract here is entities, the aspect terms, the qualifiers, and the quantifiers, right? This is what is needed to essentially understand how a sentence is being expressed, right? So, in short, what it does is when the character level STM, what it does is it produces a score of -1 to 1 for each character that it looks at a document. So in this particular review, as you can see, it started off all right, but over the time, the more characters the LSTM read, the more negative the sentiment is. So it was able to precisely tell you at what points of the sentence the review actually became more and more negative, right? I mean, this one is an extremely negative review, so it's pretty much like going from yellow all the way to the red, right? And then using aspect extraction, we are able to find out that for this particular domain of reviews or for the products, what aspects care about are things like display, email alert notification, fonts, and wallpapers. So we took all the key phrases that are around these aspects. We took the character level output, we took the character level embedding that we got, and then we simply overlapped to see which of these key phrases of these aspects is triggering the highest shifts in the delta, right? That's what you see on the right-hand side. Those are the shifts in the delta that you see when it goes from one character to another. So in this way, we are able to use a good amount of traditional NLP followed by deep learning to produce a pretty sophisticated feature like an aspect level sentiment. So when all these reviews are put together, one of the sample use cases, people want to understand if a company releases a product, which aspect of the product is being bashed by the customers when compared to what is being done well by their competitors. So when you put this in perspective, those that so-called NLP and all those enrichments, turns out to be like really beautiful, rich visual insights, right? This is essentially trying to understand for every product release, what features of the product they're doing well, what features of the product they are catching up with their competitors, right? So there are a lot of interesting insights that you can build on top of it. And the third thing is, we need connectors so that we can push these insights, right? We did some NLP, we did some drilling, but it needs to be served into external systems so that it can be useful for different product experiences that we have for our customers, right? So we have a slew of schema mappers so that we can take all this unstructured data, build insights on it, and then ship it into a data store that is relevant for a given product team that we have. And none of this would have been possible without some strong collaboration with universities. We are always open to collaborate with the best of the breed in NLP and IE. One of the things that we want to evangelize, we want to open up our platform. So far, we have been barely scratching the surface in terms of the type of insights that we can build for all the 28,000 customers we have. We are opening up enterprise solutions and our API so that other people can build applications on top of our platform. And if you want to learn more about the techniques that I mentioned, we pretty much published in all top NLP and information extraction conferences over the last 5 years or so. And we have a booth downstairs. If you have more questions, please hit us up, and you can see the presentation and the bit.ly link that has been given there. Thank you. I think I have a couple of minutes for questions, but yeah. Yes? So we are currently opening up to some beta partners right now. And we'll have, the alpha is right now, but the beta launch is in the Q1 of 2018. Yeah. Yeah. Yeah.
So you mentioned you have an open source API for NDB.
Yeah.
Do you also have something for NER?
So as part of the platform, we basically open up all the internal models that we have built over time so that you can actually programmatically access it on any type of documents. Yeah, absolutely. Yes?
So how long does it take, and how many data scientists do you have in your team to do all this data?
Yeah, so we are fundamentally a data science company, so we do have a lot. So we have, group of 35 data scientists and NLP researchers who built a lot of these applications or these pipelines, right? But the key there in accelerating the productivity of that is to have a right sort of data in the pipeline platform. And essentially that's the thing, when we want to open up these APIs, we don't want people to go through the same troubles that we have gone through in curating the external data and augmenting it with all these sophisticated NLP enrichments. It needs to be a bit more configurable so that they worry about the business logic rather than anything else.